In previous module 4, we have understood that hex or quadrilateral elements provides equivalent accuracy as that of second order TET elements, but at a lower cost. So therefore, these elements are most preferred when it comes to do FE analysis. However, there are some issues in bending problems, the way hex elements behave in pure bending. And bending is the most very much prevalent in many FEA problems, either in form of global bending or local bending. So let's see what are these issues in bending problems with hex elements, and we will also discuss the possible solutions. Before that, let's talk about pure bending problems and the characteristics. As we know, uh, this is a cantilever beam, and at the end we are applying bending moment. So this is the bending behavior, and as we know, the upper fibers of this structure undergo tensile and the bottom ones undergo compressive. So this is the stress pattern along the thickness, where the top is tensile and bottom is compressive. So these are pure bending characteristics, as we know from our solid mechanics fundamentals. The axial strains epsilon 11 or sigma 11 axial stresses, they vary linearly through thickness. So in this case, x is r, epsilon xx, and which is equal to epsilon 11. They are our bending strains, okay, axial strains. Basically, in FEA, we call it axial stresses. In solid mechanics, we call them bending stresses. And the second characteristic is that there are no shear stresses or strains, and therefore sigma 12 is equal to 0. Okay, let's try to understand this in pure bending. So this is our undeformed structure, and we can assume some lines here. Under bending moment, structure is going to deform in this fashion. So as we know, in pure bending, the lines, the perpendiculars, the lines which are perpendicular before deformation, they remain perpendicular after deformation. So that is the pure bending. And as from this we can see that the shear stresses or strains in 1-2 plane or xy plane, they are 0. Okay. Because as we know from the definition of shear strain, it is the change in angle between two perpendicular lines. Okay. So here they are remaining perpendicular, and hence we can say there are no shear stresses. And let's see if it is not pure bending, there is some shear. What happens? So this R structure, instead of applying bending moment, we are going to apply some force, shear force. So the structure will deform something like this. The fibers will be as shown here. So these are initial fiber lines before deformation. Let's take one particular element here, this element. So it undergoes a deformation something like this. Okay. So let me zoom out here. The element which was earlier of this shape will deform something like this. Okay. So there is a change in angle between these perpendicular lines. Okay. So there is a shear here. So we can say that in this case epsilon 12 or sigma 12 is not zero. So we can say this is not a pure bending. Okay, this is bending plus shear. There are bending stresses. Along with that, we also observe shear stresses. So with this concept, in coming chapters, we will see workshops and different element types issues.